Hey everyone, this is my Abstract Algebra Exam 3 Review Problems and Solutions video. We'll start with a problem related to classifying finite abelian groups, but from that point on, we'll move on to ring theory. Definitions, factual information, calculations, and proofs related to rings, integral domains, fields, ideals, polynomial rings, divisibility, irreducible polynomials and reducible polynomials for that matter, various kinds of tests, as well as general divisibility theory in integral domains. So the first question is, up to isomorphism classes, what are the abelian groups of order 72? Okay, abelian groups are much easier to classify than non-abelian groups. Second question is, how many abelian groups are there of order 2592? As you can see, in each case, I've given you the prime factorization. The prime factorization is key to helping you figure out the different isomorphism classes, and this is all based on something called the fundamental theorem of finite abelian groups. Of course, the simplest abelian group of order 72 is the cyclic one, Z72 being our prototype. As a set, those contain the integers from 0 to 71, and the group operation is addition mod 72. It is cyclic. It also is worthwhile noting that this is isomorphic to a certain external direct product of Z8 with Z9, and the reason that ends up working is because 8 and 9 are relatively prime. A new isomorphism class can be obtained from this by taking 8 and thinking of it as 2 times 4, 2 to the first times 2 squared, giving you a couple other factors in a new external direct product of Z2 with Z4 with Z9. This is not isomorphic to this because 2 and 4 are not relatively prime. Continuing in this theme, we can also think of 4 as 2 times 2 and get yet a new isomorphism class, the external direct product of Z2 with Z2 with Z2 and then with Z9. In each case, we have a new isomorphism class, and all these groups happen to have order 72, 2 cubed times 3 squared, 8 times 9. I can get 3 more isomorphism classes by thinking of 9 as 3 times 3. We would have the external direct product of Z8 with the external direct product of Z3 and itself, corresponding to this one, but not isomorphic to it. These are distinct isomorphism classes because 3 is not relatively prime to itself. Continuing, take Z2 with Z4 and then do 2 factors of Z3. Like this. And finally, take 3 factors of Z2 along with 2 factors of Z3. So altogether, we have 6 isomorphism classes for abelian groups of order 72. There they are. It's not the only way to write these. In fact, you know, this one, the cyclic one, can be written in 2 ways. You can write these other ones in other ways too, but I don't want to get into details. Second question is, how many abelian groups are there of order 2592, where that number you can check is 2 to the 5th times 3 to the 4th. Maybe I should just double check it to show you. 32 times 81, I actually had it on the calculator. 2 to the 5th times 3 to the 4th, 2592. The key thing to realize as far as the number of such isomorphism classes is you've got to look at the exponents. Think about the simpler example here where the group had order 72. We had 8, which is 2 cubed. Z8 is a certain isomorphism class. I'm focused on the first factors here. That's distinct from the external direct product of Z2 with Z4. That's distinct from the external direct product of Z2 with Z2 with Z2. In each case, the subscript of Z is a power of 2. 2 cubed, 2 to the first, 2 squared, and then 3 factors where it's a 2. Similar kind of thing happened with a 3. The exponents have to add to the number of factors of 2 and the corresponding number of factors of 3 in the prime factorization of the number that we have. 3 is one way to get 3. 8 is 2 cubed. 1 plus 2, 4 is 2 squared, is another way to get 3. 1 plus 1 plus 1 is yet another way to get 3, that exponent of the 2. Similar kind of thing happens with 3 squared 9, having 2 ways to write its exponent, either as 2 itself or 1 plus 1. Those are called partitions of those positive integers. And to answer the second question, we need to think about the partitions of 5 and 4 and how many there are. 5 can be written in, well, how many ways? Just as 5 itself, or as 4 plus 1, which is the same as 1 plus 4. We don't think about writing 1 plus 4 as a distinct possibility here. We can also write 3 plus 2. We can also write 3 plus 1 plus 1. We can also write 2 plus 2 plus 2 plus 1. 2 plus 1 plus 1 plus 1. 1, 2, 3, 4, 5, 6. I need one more, and that is 5 ones. 1 plus 1 plus 1 plus 1 plus 1. 1, 2, 3, 4, 5, 6, 7. There are 7 ways to partition 5, which again is the exponent of the 2 here. What about the number of partitions of 4? I can write 4 as itself, or as 3 plus 1, or as 2 plus 2, or as 2 plus 1 plus 1, or as 1 plus 1 plus 1 plus 1, altogether giving 5 ways to partition the positive integer 4. 7 ways here, and 5 ways here. For each one of these, as being powers of 2, you can match with each one of these ways of being powers of 3, giving you altogether 7 times 5, 35 ways to combine them, meaning there are 35 isomorphism classes of abelian groups of this order. 7 times 5, 35 isomorphism classes for abelian groups. Abelian groups, there's my abbreviation for groups, of order 2592. That's the answer. Okay, that's how you do that. All right, on to ring theory. Let R be a set with 2 binary operations, addition and multiplication. And in Gallien's book, which is what I'm using, that means closure is automatically satisfied as part of the definition of a binary operation. So we don't need to mention closure after this point. Give the rest of the definition of what it means for R to be a ring. Okay? So again, closure is taken care of with the fact that we're saying these are 2 binary operations, addition and multiplication. If your textbook author doesn't take that approach, you would want to make sure you mention closure, or if your teacher doesn't take that approach. So we want the other properties besides closure for a ring. And the thing I always remember, first of all, is that a ring is an abelian group with respect to addition. So I need to write down the properties of abelian groups. So the first thing is that it's going to be associative with respect to addition. You're going to have A plus B plus C, with the A plus B in parentheses equal to A plus, in parentheses, B plus C for all A, B, C in the ring. Upside down A there means for all. So the associative property holds. Again, rings are abelian groups with respect to addition, so we also actually have the commutative property with respect to addition. A plus B equals B plus A for all ring elements A and B. Groups also have identity elements. If you're using addition as your group operation, you would denote the identity element as 0. There exists an element 0 in R such that A plus 0, which would of course equal 0 plus A because the ring is commutative with respect to addition, 0 plus A equals A for all A in the ring. And the fourth property is that each element is going to have an additive inverse. For all elements A in the ring, there exists an additive inverse. Call it negative A, not A to the negative 1 power, because the addition is the group operation in a ring. There exists an element negative A in R such that A plus negative A, which yes will equal negative A plus A, equals the identity element 0. Okay, and I already have my universal quantifier there at the beginning. But now we have a couple new properties. One new property is you definitely want multiplication to be associative. We already have the associative property for addition. You do want multiplication to be associative. There's very few situations in math where you wouldn't want some sort of multiplication to be associative. There are some situations, but most situations, especially in abstract algebra, we do want associativity. This needs to be true for all ring elements. And finally, you need a property that connects addition and multiplication. I hope you know that's called the distributive property. A times in parentheses B plus C equals AB plus AC. We distribute the A through the parentheses. On the left, we do not assume rings are commutative with respect to multiplication in the abstract, though in many situations you do assume you have a commutative ring. So I need to write the other associative property with the A on the right separately. B plus C times A on the right equals BA plus CA for all A, B, C in the ring. Okay, so there's, again, associative property with respect to addition, commutative property with respect to addition, rings are abelian groups with respect to addition, existence of an additive identity, existence of additive inverses, associative property with respect to multiplication, and distributive property. Notice we do not assume, well, at least Galilean doesn't, that the ring has a multiplicative identity. When it does, we denote it by 1, not E as in group theory, by 1 in ring theory, and we call it a unity when it does have a 1, a multiplicative identity. We also, in part because we're not assuming multiplicative identity, do not assume multiplicative inverses. Though when they do exist, those are special and we call them units. Okay? And again, for emphasis, we do not assume the ring is commutative. When it is commutative, we call it a commutative ring. We do not say it's an abelian ring, call it a commutative ring. Number 3, let R be a commutative ring with unity 1. Commutative ring with unity 1. So again, the commutativity refers to assuming multiplication is commutative because we automatically assume addition is commutative. Unity 1, that means that's the multiplicative identity. Define what it means for an element R to be a unit in the ring. And that definition is just that R has a multiplicative inverse. R in R is a unit if there exists an element, call it R inverse in R, such that R times R inverse, which would be the same as R inverse times R because we're assuming the ring is commutative, does equal the unity 1. 1 is the unity, is the multiplicative identity in a ring. Don't denote it by E, it's traditional to denote it by 1. Okay? Though you should realize, for example, if the ring happened to be a matrix ring, which would not be commutative, it would be the identity matrix that you'd be talking about when you write the 1 there. This is what it means to be a unit. You've got a multiplicative inverse. 0 is never a unit. 0 never has a multiplicative inverse, but many other elements could. Not necessarily, but could. Fourth problem, let R be a commutative ring, and let A be an element of R that is non-zero, commutative ring. Define what it means for A to be a zero divisor. A divisor of 0, you might say. Zero divisors make ring theory kind of strange when they exist. It's kind of nice when they don't exist. Even if A doesn't happen to be a unit, it's nice if it's not a zero divisor because zero divisors ultimately help you solve equations. Not going to get into details right at the moment. Okay, that'll come later when we talk about factorization. What does it mean for A to be a zero divisor? It means A in R is a zero divisor. Notice A is not 0. If there exists some other non-zero element, there exists a B in R with B not equal to 0, such that, but you might say, A times B does equal 0. And we are assuming it's a commutative ring. That would be the same as B times A in this definition. You could talk about left or right zero divisors in non-commutative rings, but we're keeping things simple and assuming the ring is commutative. So you're multiplying two things and getting 0. An example of this, by the way, in a non-commutative ring would be like a matrix ring, a 2 by 2 matrix ring. If you squared this thing, you get the 0 matrix, which is the additive identity of a matrix ring like that, of a 2 by 2 matrices, say with integer entries. It doesn't fit this because it's not a commutative ring. An example of a commutative ring where this happens is Z4. In Z4, 2 times 2 is 0 mod 4, so 2 would be a zero divisor in that particular ring. Okay? That's what a zero divisor is. We don't like zero divisors, you might say, again. Number 5, using words and in one sentence, define what it means for a set F to be a field. I also could have put a problem in here to define what it means to be an integral domain. I'll go ahead and say what an integral domain is as a bonus here. An integral domain is a commutative ring with unity in which every non-zero element, or excuse me, is a commutative ring with unity in which there are no zero divisors. Okay, say that again. An integral domain is a commutative ring with unity in which there are no zero divisors. A field is even more specialized. And I'm just going to say the answer here. A field is a commutative ring with unity in which every non-zero element is a unit, has a multiplicative inverse. That's what we're looking for. That's a commutative ring F with unity, a 1, is a field if every non-zero element is a unit. In F is a unit. Has a multiplicative inverse, okay? I did use the word ring, unity, and unit in there. Ring, unity, and unit. Every non-zero element is a unit, has a multiplicative inverse. That does mean the set of all non-zero elements of the field turns out to be an abelian group under multiplication. When you take out 0, all the non-zero elements. 0 does mess things up as far as the entire ring being a field under multiplication. Being a field under or being a group under multiplication. But if you take out 0, then the field does become a group under multiplication. In fact, an abelian group. All right, second page. My computer's acting up here. Hopefully it'll calm down. Let R be a ring, and let A be a non-empty subset of R. Define what it means. Well, do one of two things. I will do both of them. Either define what it means for A to be an ideal of R. Technically speaking, it's a two-sided ideal because we're keeping things simple. Or state what's called the ideal test. Okay? So let's do the definition first. Initially here we're assuming A is a non-empty subset of R. Technically speaking, to make this definition as efficient as possible, we assume A is a subring, which is analogous to a subgroup. It's a subset of R that is also a ring under the ring operations of addition and multiplication. A subring, so this is the definition, A of R is an ideal of R if what? I call it superclosure. Could write it like this. If A times R is an A and R times A is an A for all little a in capital A and for all little r in capital R. The product of A times R and R times A isn't just in the ring itself, the overall bigger ring. It's in fact in the ideal, and it doesn't matter what order you do it in. Notice because I'm writing it twice there that I'm not implicitly assuming that R is commutative. So I need to write it twice if I want both of those to happen. Okay? That's what an ideal is. I call it superclosure. That's not a standard kind of terminology. That is the definition of an ideal. What is the ideal test? A non-empty subset, don't assume it's a subring necessarily. Subset A of R is an ideal of R if what happens? It's got to be closed under subtraction, which effectively means the subset is a subgroup with respect to addition, and it's got to be superclosed. If part 1, A minus B is an A for all A and B in the ring, and it's got to be superclosed. Property 2, AR and RA are in A for all, once again, little a in capital A, and for all little r in capital R. Okay? Multiply an arbitrary ring element, little r, with an arbitrary ideal element, little a, and it gets sucked into the ideal. Super closed. I like making a slurping sound. It gets sucked in like that. Okay? You can think of it that way in either with the definition or the test. That's the definition. This is the test, which is really a theorem. Number 7. Let R be a commutative ring with unity and let A be an element of capital R. Part A, use set builder notation to define what this symbol means. It's called the principal ideal generated by A. And then part B, define what it means for R to be what's called a principal ideal domain. Okay? All right, what is a principal ideal? First of all, generated by A. This notation you can see here, if you're familiar with group theory, looks like the notation for a cyclic subgroup generated by A. By the way, some books write it like this, using parentheses instead of the pointy brackets. Gallian uses pointy brackets. It does correspond to the idea of a cyclic subgroup in certain simple situations, like the integer z, for example. However, in general, it's something different. It's not all the powers of A. It's all ring multiples of A. I am assuming the ring is commutative ring to make things simpler. So RA does equal AR. So I wrote an RA, but I could have written an AR. The set of all elements RA as R varies over the ring. Again, for example, with Z, the integers, this does turn out to be the same as the cyclic subgroup generated by A. But for example, if the ring happens to be a polynomial ring, where the elements are polynomials, which is going to be our most significant example here in this test, then this is not the same as the cyclic subgroup generated by A under the group operation, which again is addition. It's something new, it's something different. In fact, it's something bigger. It's a bigger set, even though the notation is the same. Part B, let R be an integral domain. Define what it means to be a principal ideal domain. You can say an integral domain R is a principal ideal domain. I will go ahead and abbreviate it right away. PID, principal ideal domain. If what? If every ideal in R is a principal ideal. If every ideal in R, including R itself, is a principal ideal. This is analogous to the idea of a cyclic group. Not exactly the same because, again, this notation is not exactly the same, but it is analogous. By analogy, it's a similar idea to a cyclic group. In other words, principal ideal domains are supposed to be the simplest kinds of rings, you might say, as a general class. Okay? Don't overinterpret the word simplest. You might say, well, aren't fields simplest? And okay, it depends on what you mean by simple. Fields are nice, but maybe not necessarily simple. Principal ideal domains are both nice and simple. Okay, so it is analogous to the idea of a cyclic group. Number 8, let R be a commutative ring with unity, and let A be a proper ideal of R, so it's not equal to R, it's a proper subset of R, and it is also an ideal. Part A, define what it means for A to be what's called a prime ideal of R. In a commutative ring with unity, it's a more specialized definition that we're going to give. And state an equivalent condition about the factor ring or quotient ring of R by A. I sometimes say R mod A, where the elements are left cosets. Though again, since the ring is commutative, you could also think of them as right cosets. Okay, let's go ahead and start that before we do part B. What does it mean to be a prime ideal? I'm just going to tell you the definition. It is related to prime numbers in the situation where the ring is Z, but it doesn't look like it's related initially here. So A is a proper ideal. I'm assuming that already. I'm just going to write the rest of the definition. Essentially, it's if you know the product of two ring elements is in capital A, that implies that either the first element is an A or the second element is an A. That's what it means to say A is a prime ideal in R if it's first of all a proper ideal, not equal to R itself. And secondly, knowing that the product of two elements is in A implies that one or the other, or perhaps both, are in A. How is this related to prime numbers? We'll come back to that in a little bit. In fact, we'll look at it in part C here. As far as the second part of part A, what's an equivalent condition about the factor ring, also called the quotient ring, R mod A? A is a prime ideal of R if and only if the factor ring R mod A is an integral domain. Turns out to be the answer. Okay, so this first line is a definition. The second line here is really a theorem. IFF, if you're not used to that, means if and only if. Part B, define what it means for A to be a maximal ideal of R and state an equivalent condition about the factor ring R mod A. Is a new definition, but prime ideals and maximal ideals are related to each other. In some circumstances at least. So what does maximal ideal mean? It means, again, it has to be first of all a proper ideal. And it also means essentially that if you've got some inclusions of ideals, where B is an ideal here, and you're sort of initially assuming B could be strictly between A and R as far as inclusions go. If you drew a picture, if this is R and this is A is a subset of R. You're initially in this inclusion line here, we're assuming B is in between A and R, so to speak. B is bigger than A and includes A, but does not necessarily equal all of R. But we're saying A is maximal if this implies that either B equals A or B equals R. In other words, there's nothing in between A and R, you might say, in this picture. A is maximal in that sense. The equivalent, this is the definition, the equivalent condition in terms of factor rings, or again they're called quotient rings, is that A is maximal in R if and only if R mod A, that factor ring, is a field. These things are related in general because every field is an integral domain, and therefore every maximal ideal is a prime ideal. If you know you got a maximal ideal, you know this is going to be a field and therefore an integral domain, and therefore the ideal will also be a prime ideal. And in some situations, prime ideals are also maximal. If the factor ring, for example, happens to be a finite integral domain, it will automatically be a field, and therefore both of these conditions will be satisfied. Part C, let R be the integers, and let A be the principal ideal generated by 5, which does correspond to the cyclic subgroup generated by 5, and therefore will be all integer multiples of 5, including negatives. So it would include like negative 15, negative 10, negative 5, 0, 5, 10, 15, etc. Is A a prime ideal? Is A a maximal ideal? Explain. The best way to explain that is to consider the factor ring. R mod A, which is Z mod this principal ideal, turns out to be, you can verify with the first isomorphism theorem or just knowledge, isomorphic to Z5 as a ring under addition and multiplication mod 5. And because 5 is prime, this is a field and an integral domain. And again, all finite integral domains are fields. And therefore, the answer to these questions is A prime, is A maximal, is yes and yes. Therefore, yes and yes. And that's the explanation based on the theorem that is essentially, well, right there, two theorems, this one and this one. Okay, and the fact that every field is an integral domain. Number 9, let D be an integral domain. Let A be an element of D that is non-zero and not a unit. Define what it means for A to be irreducible in D. Irreducibility in general integral domains is analogous to the definition of prime for the integers. But we also are going to have prime elements in integral domains, which is a little different definition related to Euclid's lemma. Don't worry about that for the moment. A to be irreducible in D, A is irreducible if the only way to factor A is a trivial way. Just like with prime numbers, the only way to factor them is trivial. 29, for example, is just 1 times 29. There's no other factorization in terms of positive integers. How do you say that in the general integral domain here? If A equals, say, B times C, implies that B or C are somehow trivial, and the trivial elements of rings, integral domains in this context, are the units. A equaling B times C implies B or C is a unit, meaning they have multiplicative inverses. Okay? That's the only way to factor A, which means in fields, if D happens to be a field, every element is going to be irreducible. We're talking about non-zero elements, or this does not apply even, because we always assume when we're talking about this definition in the first place that we also have an element that's not a unit. So we're thinking more analogously to the integers here. Units in the integers are plus or minus 1. The unity is 1, but the units are plus or minus 1. That's the definition of irreducibility. It corresponds to our idea of prime in the integers. Number 10, identify the zero divisors in the units of the ring Z8. Is Z8 an integral domain? Is it a field? Determine the isomorphism class of the group of units. You need some experience here. First of all, 8 is not prime, so the answer to these questions is no and no. No and no. Which means there will be units. There will be zero divisors in Z8. Or I guess it doesn't necessarily imply that, but there will be. Z8 as a set happens to be 0, 1, 2, 3, 4, 5, 6, and 7. The group of units in Z8, which we'll identify first, is the same as the group U8 that we commonly talk about in group theory. The positive integers less than 8 that are relatively prime to 8, which are 1, 3, 5, and 7. That's the units. If you find the order of the non-identity elements here with respect to multiplication mod 8, 3, 5, and 7 all have order 2. 3 squared is 9, mod 8 is 1. 5 squared is 25, mod 8 is 1. 7 squared is 49, mod 8 is 1. Those all have order 2. So as a group under multiplication, this turns out to be isomorphic to the external direct product of Z2 with itself. So that's answering that question here. All we have left to do, and we've identified the units, is find the zero divisors. The non-zero numbers not in U8 are the zero divisors. 0 can't be a zero divisor because zero divisors by definition have to be non-zero elements. So the zero divisors must be whatever's left over, 2, 4, and 6. We should maybe confirm that they're zero divisors. For example, 2 and 4 are zero divisors because 2 times 4 is 0 mod 8. And 2 and 4 are both non-zero. This is times here. Is 6 truly a zero divisor? Let's see. 4 times 6 is 24. Mod 8 is 0 as well. So yes, 2, 4, and 6 are all zero divisors. Page 3. Consider a ring homomorphism from Z12 to Z20, where we assume the ring homomorphism evaluated at 1 is some element A in Z20. Use facts that must be true about the order of A as an additive group element in Z20, and the fact that A squared equals A in Z20. Why is that true? When I teach this class, I tell my students why it's true, and I'll tell you here quick as well. I'm assuming phi of 1 is A, but 1 does equal 1 times 1, And phi is assumed to be a ring homomorphism, so that's phi of 1 times phi of 1. But phi of 1 is a, so this is a times a, which is a squared. So if this is going to be a ring homomorphism, which means it's going to be operation preserving with respect to both addition and multiplication, we do need this to be true, and that whittles down the possibilities for a. And that's the goal, determine the possibilities for a. Show your work a given explanation. The order of a, first of all, a is an element in Z20, must divide the order of Z20, which is 20. This divides 20. That's Lagrange's theorem. We're talking about the order of a as an element in the additive group Z20. Lagrange in group theory implies the order of a is 1 or 2 or 4 or 5 or 10 or 20, which means a itself must be, well, I won't list out the possibilities because I want to whittle them down first. That's one list of possibilities. It also turns out the order of a, which is the order of phi of 1, must also divide the order of 1 in Z12. That's a property of group homomorphisms. The order of 1, lots of vertical lines here. The order of a, which is the order of phi of 1, must divide, this is our divide symbol, the order of 1 in Z12, excuse me, which is 12. 1 is a generator of Z12. Maybe your teacher uses O notation for order. The order of 1 is 12. That's probably a better thing to use, but that's what Galilean uses, is like absolute values. So it's got to divide 12 as well, which whittles down the possibilities. If we take these possibilities and take this fact, the order of a as an element of the additive group Z20 must be either 1 or 2 or 4. Okay, because that's the only numbers from this list that also divide 12. And that does whittle down the possibilities of a itself. Element of order 1 is 0 under the group operation of addition in Z20. 10 has order 2. 10 plus 10 is 0. There are two elements of order 4, 5 and 15. Okay? So these, we've whittled down the possibilities, but we're not done. We still haven't used this fact that a squared must equal a. When you square these things, do you always get back to themselves? No, you don't. 0 squared 0, that's fine. That gets back to itself. 10 squared, however, is 100, which is 0 mod 20. That does not get back to itself. How about 5? 5 squared is 25. Mod 20 is 5. 5 is a possibility as well as 0. How about 15? 15 squared is 225. Mod 20 is 5, not 15. So that means the final answer comes from these two. The final answer for the possibilities of a are 0 and 5. There's only two possible things that a can be if this is going to be a ring homomorphism from Z12 to Z20. If a happens to be 0, then it's going to be the trivial homomorphism that maps everything to 0. And if a happens to be 5, then the formula 1 will get mapped to 5, and you can figure out by operation preserving properties what other things get mapped to. Effectively, the formula for phi of x would be 5 times x mod 20. Number 12. We've already talked about this. Zn is an integral domain for any positive integer n. That's most definitely false. That's only true when n is a prime number. 13. The only ideals of a field F are trivial, you might say. The trivial one and F itself. That knowledge-based fact is true. I teach my students about that fact. I think it's pretty important to know. And if you don't know it's true, I'm telling you now it's true. Fields don't have any non-proper, non-trivial ideals. Okay, so that's worth knowing. Interesting to note. 14. If F is a field, then the polynomial ring with coefficients from F is a principal ideal domain. That turns out to be true. That's a theorem. In Galilean's book, I believe it's at the end of chapter 16. You can find it. Common example here would be when F is Q, the rationals, or R, the reals, or ZP, where P is a prime number. This, again, symbol represents the polynomial ring where the coefficients of the powers of x are from the field F. Next one, if D is a unique factorization domain where essentially the fundamental theorem of arithmetic holds, writing elements in unique ways as products of, you don't call them primes in general, here you call them irreducibles, then the polynomial ring is also a unique factorization where the coefficients are from D. This turns out to be true. It's a theorem. In Galilean's book, you can find it in chapter 18. There exists a unique factorization domain that is not a principal ideal domain. And 17 is related. Every unique factorization domain is a Euclidean domain. Okay, these two problems are related to the fact that every Euclidean domain, ED, is a principal ideal domain, PID, and every PID is a UFD. And this is easy to remember because it goes in alphabetical order, E before P, P before U. Every Euclidean domain is a principal ideal domain, and every principal ideal domain is a unique factorization domain, which means, in particular for 17, the answer has got to be false. Every Euclidean unique factorization domain is Euclidean domain is a false implication. Now, you might wonder, do the implications possibly go the other way? And the answer is they don't. I didn't say that, but it's related to this. The implications don't go the other way. There are unique factorization domains that are not Euclidean domains. In fact, by 16, this is maybe a better reason, there does exist a unique factorization domain that's not a principal ideal domain. That's true. And I just teach my students about this. An example of that is ZX. Turns out the polynomial ring where the coefficients are from the integers is a unique factorization domain. The analog of the fundamental theorem of arithmetic does hold. However, it's not a principal ideal domain. Not every ideal is principal. In particular, the ideal generated by the polynomial x and the constant polynomial 2 turns out to not be a principal ideal. That takes proof. I would encourage you to see if you can figure out why this is not principal. In other situations, you might be able to say that an ideal generated by 2 or 3 or 4 elements is a principal ideal and generate it just by one element. It's not obvious, but it turns out in ZX, this one is not principal. You cannot write it as a principal ideal. So yes, there does exist such a domain. Calculation problem. Use either polynomial long division or synthetic division to find the quotient q of x and remainder r of x when this polynomial is divided by this polynomial in z3x. So it's operations with the coefficients are done mod 3, with the coefficients, not the powers. If you use synthetic division, be careful to note that 2 is a 0 of g of x, not 1. That affects how you do the synthetic division. Let's do it both ways here. We're dividing g of x into f of x. So if I'm writing my long division symbolism here, here's the way I do it. Then I ask, what do I multiply by the highest power here to get the highest power there? I got to multiply x by x cubed to get x to the 4th. Put it up here. Okay? Remember, it's the coefficients that are modded by 3, not the powers. Then take x cubed and multiply it times each term here to get x to the 4th plus x cubed. Make sure I don't make a mistake here. Everything I think looks okay. Subtract x to the 4th minus x to the 4th is 0. 2x cubed minus x cubed is x cubed. Bring down everything else because you're effectively subtracting the 0. What do I need to multiply x by to get x cubed? I need to multiply it by x squared. Multiply x squared times each term. Put the answers down here. X cubed plus x squared. Subtract. These two terms cancel, and these give 2x plus 1. I need to multiply x by 2 to get 2x, so I put a plus 2. Notice there's no x term here. That happens sometimes. 2x plus 2 gives 2x plus 2 down there. Subtract. Careful. 1 minus 2, yes, is negative 1, but if we're modding by 3, that's 2 mod 3. So that means, what this means, if I've not made a mistake, is the quotient q of x is x cubed plus x squared plus 2. And the remainder r of x is a constant polynomial, that's 2. Okay. Yeah. If I was dividing by, say, x squared plus 1 instead of x plus 1, we might have gotten a remainder that's not a constant but a linear. But I am dividing by a linear here, so I do have to get a constant, it turns out, by the analog of the division algorithm. If you were doing this with synthetic division, what you do is you put the 0, 2 here, not 1, okay? This is analogous to x minus x minus 2 when you're thinking mod 3. Put the coefficients of f of x next inside here, 1, 2, 1, 2, 1, looking right there. Bring down this 1, multiply, 2 times 1 is 2, add, don't subtract. But remember to do things mod 3. 2 plus 2 is 4, mod 3 is 1. Multiply, add, 1 plus 2 is 3, mod 3 is 0. Multiply, 2 times 0 is 0, add, multiply, 2 times 2 is 4, mod 3 is 1, add, 1 plus 1 is 2. The last thing there is the remainder. And these other numbers, 1, 1, 0, and 2, correspond to the coefficients of x cubed, x squared, there's no x squared term here, x, and 2. 1, 1, 0, 2. As a final check, we could confirm our answer by multiplying g of x times q of x and then adding r of x and seeing if we get f of x at the end. Let's do that quick. G of x is x plus 1. Q of x is x cubed plus x plus 2. R of x is 2. If I simplify this and mod the coefficients by 3, do I get f of x right there? Let's just see. Multiply this out. I get x to the 4th plus x squared plus 2x. When I multiply x there times each term, then I multiply 1 times each term. 1 times x cubed is x cubed, times x is x, and times 2 is 2. Don't forget to add 2 again from over there. I get x to the 4th plus x cubed. Oh, did I make a mistake here? Looks like I made a mistake somewhere. Oh, yes, let's see. My mistakes. You caught that mistake before me. This should be an x squared. There's r of x. So this is an x squared here, making this an x cubed, making this this is still 2x. This becomes x cubed. This 1 plus x squared, this becomes an x squared. So what do I get here? So I ultimately get x to the 4th plus 2x cubed plus an x squared term from there plus 2x. 2 plus 2 mod 3 is 1. There we go. X to the 4th plus 2x cubed plus x squared plus 2x plus 1 does match f of x. Okay, I made a mistake in forgetting to put a square there. All right, keep going here. This is going to be a long video, but lots of good content I hope you find. Multi-part problem, decide whether these polynomials are reducible or irreducible over a given field. F of x equals x squared plus 2x plus 3 in z5x over z5. So with the coefficients I'm thinking of as being numbers 0 through 4. And this is degree 2. What you're hoping is this is not irreducible. You're hoping it's reducible. You're hoping if I plug in a number from z5, well, okay, since it's degree 2, it doesn't really matter. I either get 0 or I don't. If I get 0 for any of these, then it will be reducible. If I get non-zero numbers for all of them, then it will be irreducible. So it doesn't really matter what happens here. 0 squared plus 0 plus 3 is 3 non-zero. F of 1 is 1 plus 2 plus 3. 6 mod 5, excuse me, is 1 non-zero. F of 2 is 4 plus 3 is 11 mod 5 is 1, non-zero. F of 3 is 9 plus 6 plus 3 is 18. Mod 5 is 3, non-zero. And f of 4 is 16 plus 8 plus 3 is 27. Mod 5 is 2, non-zero. So since these are all non-zero, it means this polynomial has no roots in Z5. It also has degree 2. If it has degree 2 or 3 in such a situation, and you get non-zero numbers here, this means f of x is irreducible over Z5. Z5 is a field, so f of x is going to be reducible if I can factor it as a product of two smaller degree polynomials. The fact that none of these are 0 means I can't do such a factorization. So this one's irreducible. Wow, this next one looks really hard. When you see a hard-looking one like this, say with a high degree, the first thing that should probably come into your mind is Eisenstein's Criterion, and crossing your fingers and hoping that that can apply. And we teachers usually try to set things up to make it apply. What we're looking for is we're hoping we can prove it's irreducible over Q with Eisenstein's Criterion. And the typical kind of problem where you can do such a thing, you're looking for a prime P that does not divide the coefficient of the highest power. It does divide all the other coefficients, but its square does not divide the constant term. I don't want to pick 2 because 2 divides 2. Okay, so then I try 3, and then I look and see, oh yeah, all those other coefficients, 6, negative 18, 9, negative 54, and 12, are divisible by 3. And finally, 3 squared 9 does not divide the constant term. That's going to mean by Eisenstein's Criterion that this is irreducible over Q. And that's just the answer. This is irreducible over Q by, not Einstein, but Eisenstein. Eisenstein's Criterion with P equal not to 2, but to 3. 3 does not divide the coefficient there of the highest power. 3 does divide the other coefficients, 6, negative 18, 9, negative 54, and the constant term 12. But 3 squared, which is 9, does not divide the constant term 12. We can then apply Eisenstein's Criterion. It's kind of a strange little criterion, but helpful in some problems like this. There are some other problems where it's helpful where it doesn't fit immediately, but maybe if you do a certain substitution, maybe replace x with x plus 1 or x minus 3 or something, then you can apply it. But it's hard to know if it's going to work ahead of time unless it's set up to work right from the get-go. C, f of x equals 2x cubed plus 3x squared plus 2x plus 3. Polynomial in Zx over the rationals Q. We are talking about irreducibility or reducibility over fields because it's simpler in that case. This one looks hard, and it certainly is hard if you don't see the trick. One thing that should stand out to you is that these coefficients have a repeating pattern, you might say, 2, 3, 2, 3. And that's the hint that maybe I should try seeing if I can factor this by, out of the first two terms, factoring out an x squared, like this. And what's left out of the first two terms is a 2x plus 1, plus 3. But I also have a plus 2x plus 3 over there, which I can put in parentheses, and that allows me to factor out 2x plus 3. So I have factored this cubic polynomial as the product of two lower degree polynomials. That means it's reducible. I've reduced it, so to speak. Therefore, reducible over Q. Okay, I've factored it, still keeping the coefficients integers. And that's just a trick to see, okay? And so you got to learn about these tricks. They come up on some tests, so something to just be alert of. D is harder, but we can bring to our toolbox something else that's commonly taught. And it's called the mod P irreducibility test. We try taking, in this case, our cubic, and there's no clear way to use Eisenstein's criterion here. P equals 3, for example, does not work. P equals 2 does not work either. No other prime is going to work. So then you try the mod p irreducibility test where you mod the coefficients by some prime p. Which prime? Trial and error is what it takes. You hope mod 2 will work. That will certainly give us something that's still cubic. We want the new polynomial, call it f bar of x, to still be the same degree as the original polynomial. Let's try modding by 2 and seeing if it works. There's no guarantee this is going to work. You're just hoping. If it doesn't, then you might try mod 3 or you might try mod 5. But of course, on a test, that would be a lot of things to try and it would take a long time. So us teachers have to give you something that should work fairly quickly. So we'll try mod 2. Mod the coefficients by 2. We'll still get 21 mod 2 is 1, so we'll still get an x cubed. Negative 3 mod 2 is 1. 2 mod 2 is 0, so I have no linear term. 9 mod 2 is 1. There is the new polynomial in z2x that has the same degree as the original and is obtained by modding all the coefficients by 2 in this case, where 2 is prime. If I can show this is irreducible over z2, the mod p irreducibility test is going to imply that this is also irreducible over q. And since this is cubic, degree 2 or 3, 3 in this case, we can just check to see if it's got any zeros. F bar of 0 is 0 plus 1 is 1, not 0 in z2. F bar of 1 is 1 plus 1 plus 1 is 1 mod 2, also non-zero. And F bar of, that's all I have to do. It's because it's mod 2. No zeros in z2. This implies F bar of x is irreducible over z2, which by the mod p reducibility test means the original polynomial f of x is irreducible over q. Mod p, in this case where p is 2, irreducibility test. So again, you have to have these problems kind of set up for you if it's going to work out nicely. And so that's what I'm certainly doing for my students here. On to some proofs. Number 20, let F be a field, let A be an ideal in F. Prove that either A is trivial or A is all of F, non-proper. We referred to this with a true-false question earlier, but now prove it. Seems to be set up to do a proof by contradiction. Assume to the contrary that A is non-trivial and A is not all of F. Actually, let's not do it by contradiction. Let's just say assume that A is non-trivial. If by assuming A is non-trivial, I can show A is all of F, then I'm done. That makes sense? I'm trying to prove either this is true or that's true. I mean, A could be trivial, but if by assuming it's non-trivial, I can show it equals all of F, that's going to mean this final overall conclusion is true. Either A is trivial or it's all of F. So that fields have no non-trivial, non-proper ideals. No non-trivial proper ideals, I should say. So what do you do? It's not clear. Well, you got to go back to the definition of a field. A field is a commutative ring with unity in which every non-zero element is a unit. We've got to use that somehow. We also have to use what it means to be an ideal. It's superclosed. Those are the two key things to think about here. So I guess since A is not just 0, it's got a non-zero element. Therefore exists a non-zero element little a with little a and capital A. And since F is a field, A has to be a unit. Since F is a field, A is a unit. The element A is a unit, which implies A inverse exists in the ring. And what does that mean? Well, A times A inverse is 1, right? We are talking about the multiplication here. And wait a minute, the ideal is superclosed. This is in A and this is in R, therefore the product is in R. Or excuse me, in A. A is superclosed because it's an ideal. And superclosed is my terminology. So we have just proved that 1 is in A. We're trying to prove A equals F. Let B be an arbitrary element in the ring. If I can, in the field, R is F here. In the field, if I can show that arbitrary element in the field is in the ideal, I'd be done. Let B be an F. How is it going to be helpful to use the fact that 1 is in the ideal? Use superclosure again. So B equals B times 1. B is in the ring. Should have put an F here too, which is a field. And 1 is in the ideal. The ideal is superclosed. This is in the ideal. We're done. Therefore, F is a subset of A. We already know that A is a subset of F. Therefore, A equals F, and we're done. That's what we wanted to show. Okay? It's a fact worth knowing, too. 21. Prove that the intersection I sub alpha of any collection of ideals in R is also an ideal in R. We need to use the ideal test, which effectively is essentially equivalent to the definition, but except with the closure with respect to subtraction, you are also proving it's a subring to begin with. It's not that much different from the definition of an ideal. So first we want to prove that the intersection is non-empty. We are talking about non-empty sets here. You might wonder, what does this symbolism represent? This is your collection of ideals, I sub alpha, as alpha varies over some index set. What's that? That's a capital omega. Looks like a horseshoe. Capital omega. What is capital omega? It doesn't matter. Just some set. This is any collection here. Could even be an uncountable collection. Why is 0 in the intersection? Because it's in every I alpha. That's why. I alpha being an ideal for all alpha in omega implies 0 is in I alpha for all alpha in omega, which by definition of intersection means 0 is in the intersection. Intersection of all the I alphas, because it's in every I alpha. Therefore, this intersection is non-empty. Don't let this notation bother you here. Focus on the key ideas. I mean, you could do 2 sets and the intersection of 2 sets if you wanted to, but this does emphasize any intersection will work. To be in the intersection of all the sets means you are in every set. So the intersection is non-empty. Now let's prove it's closed under subtraction. Let little a and little b be in the intersection. What does that imply? That implies little a and little b are in each I alpha for all alpha in omega. It's important to do the quantifiers here. It's essential to do them. That's what it means to be in the intersection. It means you're in every set that is being intersected. And each I alpha is an ideal for each alpha. Implies, well, okay, let's just do subtraction. A minus b is in each I alpha. Which implies A minus B is in the intersection. It's that easy. Well, maybe I shouldn't say easy, but it's that quick. Because that's what it means to be in the intersection. So it's closed under subtraction. And now let little r be a general ring element. We need to show it's super closed under multiplication in both directions. Once again, I alpha being an ideal for all alpha in omega is enough to imply that both RA and AR are in each I alpha, which implies that each RA and AR is in the intersection because they are in every I alpha. And that's it. It really is that straightforward and that quick. You just have to understand the key ideas. What does it mean to be at the intersection? It means you are in every single one of those sets. It doesn't matter what the omega is. It's irrelevant. It's just some index set. Could be a finite set, could be an infinite set, could be uncountably infinite. It doesn't matter. The intersection is still going to be an ideal. We are using the ideal test. Another mod P irreducibility test application here. But this one's more complicated, so I separated it out onto another page. Because now we're looking at a fourth degree, not a second or third degree. I'm trying to show it's irreducible over Q. I'm saying use the mod P irreducibility test with P equal to 2 to do that. Technically speaking, my students should write sentences, but I will just write things down without sentences. So we need to mod by 2, mod the coefficients by 2, not the powers. F bar of x, first coefficient is 1, so that stays the same. There's no x cubed or x squared terms, so they stay not there. 7x mod 2 becomes x, and 3 mod 2 becomes 1. If this has no zeros in Z2, and Z2 is a field, what that's going to mean, because the degree now is bigger than 3, is it doesn't necessarily mean right away that this is irreducible. What it means is it would have no linear or cubic factors. No linear factors because no element in Z2 is a root, and therefore also no cubic factors because if you had a cubic factor, you'd have a linear factor. But what else needs to be done after that point, because the degree is 4, is why are there no quadratic factors? It's easy to show that there's no roots and therefore no linear or cubic factors. But why are there no quadratic factors? I should say here in Z2x, polynomial ring with coefficients in Z2. Why are there no quadratics? The possible quadratic factors are very limited because the coefficients must be modded by 2. Possible quadratic factors include x squared plus 1, x squared plus x, and x squared plus x plus 1. There are no others. There's only 4 possibilities here because the coefficients are either all 0 or 1, and these have to be quadratic. So the x squared terms have to be there in each case. If we were doing mod 3, there's a fair number more because the coefficients could be 0, 1, or 2, but again, the coefficient of the highest power has to be there. It has to be non-zero. However, we can rule out 3 of these right away. You can rule these 3 out right away. Why? Because they have zeros in Z2. So they are reducible in Z2. I'll just say they have zeros in Z2. Whereas F bar does not. 0 squared, 0. 1 squared plus 1 is 0, mod 2. 0 squared plus 0 is 0, and also 1 squared plus 1 is 0. The rule is out right away. Rule out. So the only one you really have to think about is this one. This doesn't have any zeros in Z2. Neither 0 nor 1. Why can it not be a factor of this 4th degree polynomial? And that can be confirmed with long division. Divide this thing into that and see that you get a non-zero remainder. Let's see if that happens. Dividing x squared plus x plus 1 into the original polynomial x to the fourth plus 7x plus 3. I cannot use synthetic division here because I'm not dividing by a linear polynomial. Got to use long division. My goal is to show the remainder of this is non-zero. And that'll mean this is not a factor of that. Oops. Do it again. I'm in Z2. X to the fourth plus x plus 1. We are working in Z2 with mod 2 arithmetic. I'm looking at f bar of x here, actually. So do your long division. X squared times x squared gives you x to the fourth. Then x squared times each term here gives you x to the fourth plus x cubed plus x squared. Subtract. But remember, minus 1 equals 1 mod 2. So negative x cubed mod 2 becomes positive x cubed. The difference there is 0. Negative x squared mod 2 becomes positive x squared. Bring the x and the 1 down as well. What do I multiply x squared by to get x cubed? I multiply it by x. Now multiply times every term. Subtract. I'm down to that thing that has a lower degree than this. This is the remainder. It's non-zero, and that's the important thing, the fact that it's non-zero. Therefore, x squared plus x plus 1 is not a factor of x to the fourth plus x plus 1 in Z2x. We already saw it had no linear or cubic factors either. Therefore, x to the fourth plus x plus 1, which was our f bar of x, is irreducible over Z2. And therefore, the original polynomial f of x, which was x to the fourth plus 7x plus 3, is irreducible over the rationals. That's the mod p irreducibility test at the very end, with p equal to 2. Okay, so that's the outline of how to do all that. Two more pages. This one involving calculations for the most part, and the next one involving a fairly short proof. So we're almost done. F of x is x squared plus x plus 2 in Z3x, polynomial ring with coefficients in Z3. Degree is 2, and Z3 is a field because 3 is prime. Part A. Briefly explain why f of x is irreducible over Z3. Similar kind of things that we've been doing recently. It's degree 2, so it's going to be good enough to show it has no zeros in Z3. F of 0 is 2, which is non-zero. F of 1 is 1 plus 1 plus 2. Looking up here is 4. Mod 3 is 1, non-zero. And f of 2, I also have to check, is 4 plus 2 plus 2 is 8, is 2, non-zero. We're doing mod 3 arithmetic there. Degree is 2. Z3 is a field. Therefore, f of x is irreducible over Z3. Part B. Based on the fact that it is irreducible over Z3, why is this principal ideal a maximal ideal in this polynomial ring? That's a fact to know. Or is it? Not why. The why is a theorem, okay? The answer is yes. When your polynomial is irreducible over a field, then the principal ideal generated by that polynomial will be maximal in the corresponding polynomial ring. That is a fact to know, an important fact to know, in fact, because of part C. This is going to be ways to generate finite fields, and will come up on the final exam review. That's a theorem. Okay? Irreducible polynomial over a field. principal ideal generated by that irreducible polynomial will be a maximal ideal in the corresponding polynomial ring. Z3 is a field. Z3x is not a field. It's a ring. Okay? Sorry about the noise. My colleagues are very loud when they're talkative. Part C, is this factor ring a field? This is a fact to know as well. Just yes. Okay, in fact, it's a fact we've already talked about maybe an hour ago. When you mod a polynomial, well, R mod A, that factor ring, when R is a commutative ring with unity, is a field if and only if A is maximal. That was the theorem. It's a field if and only if A is maximal. And this is the main place where we apply that theorem. That's the theorem 2. Part D. Use the long division or this fact to determine A and B and Z3 so that this is true. What's going on here? What's going to happen is in this field, even though f of x did not have a root in Z3, in this field, f of x is going to have a root, it turns out. Essentially, you're going to be able to say that the left coset, f of x plus a, where a is the principal ideal generated by f of x, is the trivial ideal, because the f of x gets sucked into that coset there, the ideal. So it is the trivial ideal. Lots of things I'm writing there. They're all the same. And what that essentially means is, without going into details, is f of x does have a root in this field. Okay? Now f of x is x squared plus x plus 2. And by the way, the root is ultimately going to be x plus a. That left coset x plus a is going to be the root, or at least one root. And so what this means is you can effectively subtract x and subtract 2 from both sides of this equality to say that this is true, that this equals that. And then because the coefficients can be modded by 3, we can say this equals this. Negative 1 mod 3 is 2. Negative 2 mod 3 is 1. And that helps me figure out the answer to this question. How? Let's do it with the second approach first, and then we'll also try it with long division. X cubed plus a. How can that be thought of? That can be thought of as x times x squared plus a. And by the definition of quotient multiplication, that's the same as x plus a times x squared plus a, because you multiply cosets by multiplying their representatives. So I'm undoing that here. But then again, x squared plus a, by what I have here, can be replaced by 2x plus 1 plus a. And then that could be multiplied out again to multiply the representatives. 2x squared plus x plus a. And then, continuing, I can replace the x squared with 2x plus 1 again. I mean, it's not the exact same looking thing as you see up here. You might be wondering, where's the plus a, for example. But effectively, you can do that. You can replace the x squared there with 2x plus 1 there because of what's going on here. So I'm working with the representatives of the cosets, and that's okay. I'm effectively doing coset operations here in what you might call a little bit of a sloppy way, but it works. Multiply the 2 through, I get 4x plus 2 plus x plus a, which is 5x plus 2 plus a, mod everything by 3. 5 mod 3 is 2. 2 mod 3 is 2. If I've not made a mistake, this is the answer. So the little a and the little b are both 2. Let's confirm it with long division. How? Divide x cubed by f of x. And then use properties of ideals. I'm dividing x squared plus x plus 2, f of x, into the higher degree thing, x cubed. X squared needs to be multiplied by x. Put an x up here. Multiply x times every term. Put the answer down here. Subtract, but then mod by 3. Not done. I have to multiply x squared by 2 to get 2x squared plus 1. To get 2x squared, I should say. Multiply 2 by everything. Subtract. Mod by 3. There's your remainder. Did I make a mistake somewhere? Oh, I think I made a mistake somewhere. Somewhere there's a mistake. The remainder is supposed to be the answer. So somewhere there's a mistake. I will pause the video and come back after I found my mistake. I found 2 mistakes. I already crossed off one of them. This 2 should have been 4 because 2 times 2 is 4. Then I'll mod it by 3. And this 1 here should have been 1 times x. This should have been an x. So this is ultimately going to give me now a remainder of x minus 2x is negative x minus 4, and then mod by 3. That becomes 2x plus 2, which matches that right there. That is the remainder. Why does that have to be the answer? The reason is because when we write, so that what this means is that x cubed can be written as x squared plus x plus 2 times x plus 2. There's your thing you were dividing by, there's your quotient, plus this remainder, 2x plus 2. And if I think of these as coset representatives, with a plus a here and a plus a here, this part right there gets sucked into the a because a is the principal ideal generated by x squared plus x plus 2, and that is a multiple, a ring, polynomial ring multiple of x squared plus x plus 2. That's why it gets sucked in there. So this becomes the same as 2x plus 2 plus a, confirming the answer that I got over here. Okay? Sorry about the mistake. Or mistakes, I should say. Part E, find the multiplicative inverse of x plus a in this ring. So we need to multiply x plus a times an arbitrary element in the factor ring, call it ax plus b plus a. I can write all my elements in as a linear polynomial plus the capital A, which is the principal ideal generated by x squared plus x plus 2, essentially by generalizing what we did in part D. So the goal is to figure out little a and little b to make this equal to 1 plus a, which is the unity of the factor ring. Multiply this out by multiplying representatives. X times ax is ax squared. X times b is plus bx. Use the fact that x squared can be replaced by 2x plus 1. Simplify. The x term is 2a plus b times x, and the constant term is a plus little a. I want to set this equal to the unity, which is going to be 1 plus a. The only way that's going to happen is if the system of equations holds. The coefficient of x, 2a plus b, must be 0, and the constant term a must be 1. A being 1, from this second equation implies that 2 plus b equals 0, so b is minus 2, mod 3 is 1. So it looks like, if I've not made a mistake, which is a big question mark now, I think, that the multiplicative inverse of x plus a, which is going to be a unit because this is a field we're working with, is going to be, coefficients are both 1 here, x plus 1 plus a. That'll be the answer. I should maybe do a quick double check over here, say x plus a times x plus 1 plus a becomes x squared plus x plus a. Replace x squared with 2x plus 1. 3x gives you 0. Mod 3, this simplifies to 1 plus a, which is the unity. So it checks this is correct. Yay. On to the last problem. I'm as happy as you are. Oh, it's a hard-looking problem. It's not as hard as it looks. It would be hard if I was doing full generality here. But I do teach my students about this. We're considering this integral domain z adjoin root negative 5. What does that represent? As a set, it represents all numbers of the form a plus b times the square root of negative 5, where a and b are integers. And yes, you could think of that as a subset of the complex plane. You could think of this as square root of 5 times the imaginary unit I, where I squared is negative 1. But you don't have to. Okay? This integral domain turns out to be, well, it is an integral domain, so in that sense it's nice, but it turns out to not be a unique factorization domain, so that's not so nice. I want to see why here. It's got this norm, it's called. What is the norm? Well, it's a function from this set to the non-negative integers with certain properties, certain nice properties. N of x equals 0 if and only if x is 0, where x would represent an entire expression like this. It's multiplicative, you might say. N of x times y is n of x times n of y. This is kind of generalizing absolute value in a sense. X is a unit, has a multiplicative inverse in this ring if and only if n of x is 1. And if n of x is a prime number as a positive integer, then x is an irreducible element of D. Okay, that's some background properties that my students all know about, they learn about. Claim that this is not a unique factorization domain. For example, we claim that 21 has 2 factorizations in terms of irreducibles. It's 3 times 7, or 3 and 7 will be irreducible. And it's also this product where these two things will be irreducible. 2 distinct factorizations into irreducibles. And those things, the 3 and the 7 and these 2 things are not going to be units. They will be irreducibles. Suppose, to keep things simple, you've already proved that these things are all irreducibles. Here's your task. Finish the proof by proving this thing is also irreducible. Turns out property D, even though I mentioned it here, is not helpful, not directly applicable. If n of x, the value of the norm at x is a prime number, then x itself is irreducible. That's not something we're going to be able to use here, because n of this thing will not be a prime number. But properties B and C will be helpful. These 2 properties are going to be helpful. Essentially, it's an argument by contradiction. First note, what is n of this quantity? 1 plus 2 root negative 5. Use the formula here. A is 1, B is 2. So the formula says do 1 squared plus 5 times 2 squared. 1 plus 20 is 21. Maybe not a coincidence there. 21 is what these 2 things multiply to. Let's also note that 21 is 3 times 7, an ordinary prime factorization. Let's suppose, for the sake of getting a contradiction, that 1 plus 2 times root of negative 5, I'm trying to show it's irreducible. Let's pretend it is reducible. That is x times y, where x and y are in this ring, are, let's assume, are not units. Trying to get a contradiction out of this. I'm essentially assuming that this thing is reducible. How do you get a contradiction? We also need property B and property C again. We know by the note up here that 21 is, which is 3 times 7, is the norm of 1 plus 2 root negative 5, which will be the norm of x times y, since I'm assuming x times y is 1 plus 2 times root 5, negative 5. And by property B, that's going to be the same as n of x times n of y. N of x and n of y are positive integers. This is 21, this product. Here's the question. Is that possible? Since x and y are not units, this is an if and only if n of x and n of y can't be 1. X and y not units implies n of x is not equal to 1 and n of y is not equal to 1. Therefore, either n of x equals 3 and n of y equals 7, or n of x equals 7 and n of y equals 3. And in either case, you get a contradiction. These things, the norm values do have to be positive, non-negative, I should say. They can't be negative 3 and negative 7, for example, although we could get contradictions out of that too, perhaps. In either case, you get a contradiction. Let's say x is a plus b times root negative 5. By the formula for the norm, that's a squared plus 5b squared. We could do a similar argument if n of y equals 3. We're saying this equals 3. That's impossible. A and b have to be integers. There's no way this can be 3. This is certainly greater than or equal to 0. It can't be negative, no matter whether a and b are positive or negative. And just try it out. Think about it. If b is positive, for example, or if b is non-zero, then already 5b squared is bigger than 3. And adding a squared to it's not going to make it go down to 3. So b would have to be 0, but that would imply a squared is 3. But a is an integer. There's no way its square is going to be 3. The square root of 3 is not an integer. That's a contradiction. Okay, and you could make the same argument whether you assume n of x is 3 or n of y is 3. This being a contradiction means our original supposition to the contrary, that this is factorable in terms of non-units, must be false. We must therefore conclude that x or y is a unit, which means 1 plus 2 times root negative 5 is irreducible in D. That's what we were trying to do. Prove that this is irreducible in D, and that would finish the proof. Okay, and you can write that down. Have a good day.